Hello and welcome to today's webinar presented by Dlubal Software. Today we will once again be working in our finite element analysis and design software RFEM. The title for today's webinar is AISC 360 Steel Member Design in RFEM. My name is Amy Heilig. I'll be your presenter today. I'm the CEO of the U.S. office located in Philadelphia, Pennsylvania. I'm also a technical support and sales engineer. My colleague Wieland Gotzler will be your moderator, answering any questions that you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in the way of the presentation when you logged into this GoToMeeting, you can feel free to hide that or show that control panel with the orange arrow up at the top. We always want to encourage everyone to ask questions during the presentation. You can do so within this same dialog box. If by chance I cannot get to your question or my colleague Wieland can't, I'll certainly send you a follow-up email afterwards. As far as the content today, I want to quickly go over what we'll be discussing over the next hour. The first bullet point here is I want to show you a little bit about RFEM. This is our main program where we'll be showing you how to model, to load the structure, and to run a full analysis of our AISC steel members. I really want to focus on the direct analysis method today from Chapter C in the code, mainly in RFEM. This is in comparison to the effective length method, which we'll discuss some of those differences later on. And then we'll jump into our add-on module, RF-STEEL AISC. And here we'll do an ultimate and serviceability limit state design for our steel members according to the AISC 360 2010 edition. We'll also take a look at a detailed review of the code checks within the add-on module and also show you how to do member optimization based on those particular code checks. So for those of you who are not familiar with our program, RFEM is the main program. This is where we're going to be doing all of our modeling. We integrate with other BIM software such as Revit, Tekla, AutoCAD. You'll load your structure here and you'll also address load combinations according to a particular standard. And you can run a full analysis. So therefore, you're going to get any of your design internal forces directly from RFEM. This includes things like stresses, internal forces, deformations, support reactions. And from here, we'll actually take these design internal forces and bring them into our add-on module, RF-STEEL AISC. Within this add-on module, we actually take all of the information from RFEM, such as materials, sections, the loading that we had already done, and we'll take those and do an ultimate and serviceability limit state design. But we also need to verify some additional information that's related to our code checks, such as things like unbraced lengths, giving the add-on module the limiting deflection ratios for our deflection check, and this is also where we will be doing the optimization of our structure. In the 2010 edition of the AISC, in Chapter C, like I mentioned, we'll be focusing on today with the direct analysis method. This is in comparison to the effective length method in Appendix 7. Back in the 2005 edition, these were actually flip-flopped. The effective length method was in Chapter C and direct analysis method was in Appendix 7. To me, this kind of tells you that maybe this is the direction that a lot of engineers are headed, more so towards a direct analysis method rather than effective length. We do have the option to do both in the program, so I will show you today focusing on the direct analysis method. Section C1 gives us 5 stability requirements. Those 5 requirements include number 1 here, flexural, shear, and axial member deformations. Well, this is in RFEM alone with the analysis. We also need to include second order effects, P delta and P little delta, which we'll discuss in our next slide. We want to take into account geometric imperfections. We want to take a look at stiffness reduction and how that's handled in the program, as well as uncertainty in stiffness and strength. So with that, we can jump into our RFEM model. So those of you who are not familiar with the program, this is RFEM. This is the main program where, for the purpose of saving a little bit of time here, I went ahead and modeled a 3D steel hull. We have our tables that we can work with down here at the bottom. We have our project navigator, which you'll see me in quite a bit today, as well as our tools up at the top. As far as our structure goes, as you can see, it's just basically our steel members from the AISC. We have some columns here that are typical W shapes. These are moment frames looking in the global X direction. I have some smaller columns here that are HSS members. I have these purlins filling in between our moment beams, HSS members as well. And lastly, I have some lateral bracing here that are single angle members. I also used our load combination generator to basically produce the AISC E7 load combinations, which we'll take a look at in just a minute, but you can see them all populated here. As far as the applied loads, I did use our load generator, area loads on members, to create a dead load at our roof height here. Now you can see that I can always right-click and display separately, and I did so that it is a one-way load distribution on our purlin members only. Same thing goes for the live load, just maybe a little bit smaller of a magnitude here. Now I can always just click the display separately again to view them more so as an area load. And lastly, I used our load generator for our wind loads. This is available under Tools, Generate Loads. We have both snow loads and wind loads here, and we can take into account both the walls and the roof according to AISC E7. Now, this is for pretty general type structures, as you can see from this picture here. The minute that you're kind of getting outside of these rectangular shapes for building type purposes is when you'll need to manually apply those loads in RFEM. For this particular case, I only did apply case 3 from the AISC E7. We can also apply case 1 and minimum wind loads as well. Just to keep things a little bit more simple, I've only applied case 3 though, so just keep that in mind. With case 3, we then have 4 wind load cases that are generated automatically, which you can see here. So with that, I can jump into my load cases and combinations. And just like you saw graphically, here is our dead load, our live load, and our 4 wind load cases. I can take a look at my combination expressions, and because I use automatic wind load generation from the AISC E7, I have my LRFD load equations and my AISD load equations that were created automatically. If I press this little info button here, I can see exactly what the AISD load combinations that the program is going to address, as well as the LRFD. So under the load combinations tab, this is where our individual load combinations are listed out. You can see here that the orange are categorized according to our LRFD equations, and then we have the red for our AISD equations. What is nice though is that under my load cases, I've only defined dead load, live load, and wind load. You can see under action categories, we have rain, we have snow, we have earthquake, but the program filters out all those unnecessary load cases so that we're only looking at the relevant loads. So that's nice, we're not having to filter through all those other load cases in order to apply those to our structures. Our result combinations here are nothing more than an envelope solution for our LRFD and our AISD load combinations. Back under the load combinations tab and calculation parameters, you'll notice that we have a few different methods of analysis here. So the default is actually second order analysis in the program, P delta and P little delta, and this is what I briefly explained in the PowerPoint. We can also run according to a geometrically linear analysis, and a large deformation analysis is maybe when you would have cable members in your structure would require such an analysis. So as I mentioned, the default for all of these load combinations is second order analysis. Jumping back to the PowerPoint, let's discuss a little bit about P delta and P little delta. So as engineers, if we're following the code, and not even in addition to the steel code, but a lot of other materials as well, require some type of second order analysis with this P delta effect taken into account. And as you can see from this picture, P delta is where an axial load is applied to our vertical members And for the first iteration, we're going to get some deformation of the structure. That's what we would call delta. So when we're looking at the second iteration, this axial load is now acting on the deformed structure, so we inevitably have a higher bending moment along these members that comes from P multiplied by delta. So in RFEM, we actually create the deformed system stiffness matrix for every iteration. We are a nonlinear analysis program, so instead of applying fictitious shear loads at the top or bottom of the members, we will just create that stiffness matrix based on that deformed structure for every iteration. Now you can set the number of iterations as well as the tolerance in RFEM. I'll show you that in just a minute. P little delta. This we may not be as familiar with. P little delta is a destabilizing effect of member curvature. Again, we can take a look at this picture to kind of view what P little delta actually entails. And it's taking into account the smaller deformation along the member's curvature. Now there is criteria in the code under section C 2.12 that we can neglect P little delta. Typically with a lot of cases, P little delta really doesn't have that much effect on your structure. Now this really is the engineer's discretion, but the nice thing about RFEM is that with that second order analysis, we will always include P little delta. Now some other programs require you to add additional nodes along the member to take that into account, but again with our program, you don't need to do all of that. It's automatically considered when we're running that second order analysis. So jumping back to the program, you can see here second order analysis, and it's very clear that we're running both P delta and P little delta. If I go into calculate and calculation parameters, this is where we can control our iteration and our tolerance settings for P delta and basically any nonlinear analysis within the program. So the default set for max number of iterations is 100. That's a fairly good number. Now, when we are talking about precision and tolerance, we give you a range if you check this box from 0.01 to 100. This isn't necessarily a percentage. There's so much that goes into this nonlinear analysis that we kind of give you this range from 0.01 to 100 with the lower end of this factor being more exact. When we're getting up towards the 100 range, well, this is going to be much less exact. So what the program will do is it will iterate until we're reaching somewhere along this range that we have set. And you can see that the default is set at 1.0. The problem being the lower factor we go here to get a more exact answer, the longer the solve time. And if you set this too high, well, then you might not have accurate results. So again, default is set at 1.0. Typically, you're not going to touch this. So that's why we have this grayed out as it is. Max number of iterations, you may get a warning in the program when you run an analysis telling you that the max number of iterations has been met, but yet we can't converge. Well, that's something where maybe you could come in and add maybe more iterations here, something like 200, 300. Again, this is going to increase your solve time, but if you're having an issue with converging, then that's probably the way you want to go, or you just want to look at the overall stability of your structure. Like I said, you can go ahead and adjust these factors, but most likely, unless you really know what you're doing, you probably will not be in this precision and tolerance section here. So that essentially covers P delta and the second order analysis within the program. Jumping back to the PowerPoint, the second item from Chapter C is geometric imperfections. And I want to discuss a little bit about how RFEM can handle this. So the consideration of initial imperfections comes from section C 2.2. And the code really tells it that this is more so to address column out of plumbness. When we're looking at member out of straightness, this is more so addressed in Chapter E for our compression members. So addressing column out of plumbness, we have a couple options for this. We can either directly model the imperfection. This comes from section C 2.2a. Earlier this year, I did a previous webinar. It's called AISC Advanced Steel Design in RFEM. You can find it, the recorded version, on our website at dlubal.com. If you are interested to see this application of directly modeling the initial imperfections, then this is a great webinar to refer to. Because today, rather, we're going to use notional loads from section C 2.2b to address the initial imperfections. So you can see that this screenshot here is directly from the AISC code. And we have this equation for our notional loads to basically take into account the initial imperfections. The n sub I is our notional load at level I, so basically we need to apply these to every single level. 0.002, this comes from the AISC Code of Standard Practice, the L/500. We also have an alpha factor here for LRFD and ASD, and then Y sub I is our gravity load applied at that level, so any type of vertical load. So you can understand that our notional loads are really dependent on the applied load for that particular load case or load combination. The code also tells us that we need to consider 4 different notional load cases. We have 2 orthogonal directions and both positive and negative. So in accordance to RFEM, this would be both positive and negative X direction and Y direction. As I mentioned, the 0.002 comes from the AISC Code of Standard Practice for L/500. The code does tell us that if we feel that we would like to adjust this for whatever reason, we can do so, but this is the suggestions directly from the AISC. Something else very interesting to note here. So a lot of us engineers probably don't deal much with notional loads, and maybe we don't know the reason why we don't apply notional loads. Well, the code tells us in section C 2.2b that if our max second order drift over max first order drift is less than or equal to 1.7, then we only have to apply these notional loads to our gravity only load combinations. So any other load combination that has maybe wind or earthquake or any other type of lateral load, we can completely disregard these notional loads. So how does that apply to RFEM? Well, if I go back to my load combinations dialog box here and I choose calculation parameters, I would want to choose all of my LRFD load combinations by hitting my control button and selecting all the LRFD. I would want to run these according to a geometrically linear analysis. Now I'd want to take a look at my drift of this first level. Drift, as we know, is not just purely deformation. It is dependent on our story height. So for one story, really doesn't matter, but when you're getting into multiple levels, drift is not so easy at just taking a look at deformation of one height versus the other, but you also need to take into consideration the different height levels. We don't have a table for drift at the moment. That is something that we do plan to implement into the program. But quite honestly, it's not that hard to pull your drift information. Like I said, we'd want to run these first LRFD load combinations according to a geometrically linear analysis. I could take a look at 1 or 2 or a handful of nodes at this top roof level. Then I'd want to rerun these load combinations according to a second order analysis and take a look at the deformations or the deflections at this first level and compare it to my linear analysis. So what the code's telling me is that if my drift of my second order analysis over my first order analysis is less than or equal to 1.7, then that's when I can disregard my notional loads with lateral loads being applied for that load combination. Now I can tell you that 1.7 is a pretty high ratio. I think that for most structures, I won't say all because this is certainly something that you would want to check for yourself, you will not come very close to that 1.7 ratio. For example, this structure, I ran it and I think I was at 1.4 0.13 or something like that. So therefore, that tells me that I don't need to apply my notional loads to any of these load combinations that have wind load in them. But you'll notice that my first two load combinations for dead load and live load, well, these are gravity-only loads. So therefore, technically, I do need to apply these imperfections to those particular load combinations. So how do we do that? Well, back under load cases, I'm going to create a new load case. And under the action category, we have this option imperfection down at the bottom. I can give this load case a description, so we will call this imperfection positive X. I'm going to create a copy of this and rename it to negative X. Create another copy as positive Y. And one more copy as negative Y. Now, as I just showed you in the PowerPoint, the code does require two orthogonal directions as well as positive and negative. So that's what we're addressing here with our 4 different imperfection cases. So now that we have applied these different imperfections, to the load cases, we need to somehow implement them into our load combinations. If I look at my load combinations, I still don't see any type of imperfection here. So how can I apply these to my load combinations? Well, under combination expressions for LRFD, there's an option for imperfection load cases here. If I check this checkbox, then automatically this settings dialog box pops up. And here are my 4 imperfections that I just created. Now I'm going to uncheck a couple of these options. Now what I do want to have check is I want all imperfection load cases as alternative, meaning I don't want them to act at the same time. I want to treat each one individually, not as additive. This other option, subject to specific load cases, well, this is where I'm going to tell the program to automatically insert these into the load combinations, but never to include them with my lateral loads. So how do I do that? Well, there's a button here with 3 dots, and that brings up select load cases. Well, now I can select my lateral loads here for wind load. So notice the only ones I'm leaving unchecked are my gravity loads, dead load and live load. I click OK. So now this imperfection positive X will be excluded with any load combinations that contain those wind loads. If I press the down key, just like what we would do in Excel, and a quick trick, if I hit the F8 key, it will actually copy the entries from the cell above. So I don't need to necessarily go in and redefine these in that additional dialog box. So now that I've kind of given it some criteria on how to apply it to my load combinations, I also want to check this checkbox here differently for each combination expression. And the reason for this is I don't want to apply these imperfections to my ASD load combinations. My ASD load combinations I'm going to use for deflection only, so I really only want to use the imperfections for my design purposes for LRFD. So now you'll notice that because I've checked this differently, my imperfection load cases ASD is unchecked. So now let's take a look at our load combinations. You'll notice we have the 1.4 dead, but now we have 4 additional load combinations, including imperfection 1, 2, 3, and 4, all treated separately. The same goes for 1.2 dead plus 1.6 live. And then we have the 4 additional imperfections. But the minute that we take into account that lateral wind load, I have no imperfections applied to these load combinations. This is exactly what I wanted. I wanted the program to filter out those imperfections and only apply to my gravity-only load combinations. If I scroll down here to my ASD load combinations, I don't have any imperfections applied to them at all. Again, this is exactly what I wanted. So you can imagine when you have a ton of load combinations, this is a very useful feature. The program has a lot of automatic features that you don't necessarily need to go in here and add them in manually. Now for each of these load combinations, we are still running them according to a second order p-delta analysis. So now that we have applied them to our load combinations, I want to select it from my drop-down box here, imperfection in the X direction. Well, so I've applied them to my load combinations, but I haven't exactly applied them to my structure. So now we want to do so. So as the code mentions, I only want to apply them to my column out of plumbness is really what we're looking at. So I'm going to highlight all of my column members, and if I hold down my control key, then I can unselect my braces here, just like what we would do in AutoCAD. I can create a new user-defined view here, visibility by selected objects, and under my Views tab in my Project Navigator, at the click of a button here, I can create a new user-defined view. So this one, we can title it Columns. So now if I were to ever get out of this view by canceling my visibility mode, I'm doing other things, and I want to go back to my columns, well, now that's available right here. And you can create as many user-defined views as you would like. So for our imperfection in the positive X direction, I want to make sure that this is what's available in this drop-down box here. Under Insert, Loads, Imperfection, I'm going to choose Graphically. And you'll see that my list of members that I just highlighted are available in this list here. And this should look pretty familiar because this drop-down, I've selected AISC 360, 2010, current loading. Well, this is the equation for notional loads. We even give you the code reference according to C2.2b. Here's my 0.002 factor. We do allow you to modify that if you choose to do so. We have our alpha factor according to LRFD or ASD. And then our YI. YI is going to be those gravity loads, our dead load and live load, applied in our structure. So again, the notional loads really depend on the loads being applied to the structure. We also have the option down here for precamber. So if you did want to put in some type of precamber for the structure that's also dependent on your axial loads, then you could do so. For our case, we're going to leave this as 0 and only apply this so-called out of plumbness. Now, we will want to apply in the local axis direction, local Z. So I'm going to click OK, and something that may be helpful if I right-click and turn on my local axes and my members. I'm going to also turn this into the wireframe view. Now we can scroll in here. Here's my imperfection. It's telling me 0.002 LRFD. This is that out of plumbness that we're going to take into account for those gravity-only load combinations. I'm going to scroll over to negative X. I need to highlight my members again, and again go to Insert, Loads, Imperfections graphically. And instead of a positive 0.002 to account for the negative direction, all we need to do is put in a negative 0.002 factor here, and we have our imperfections in the negative global X direction. I'm going to do so again with the positive Y direction, Insert, Loads, Imperfections graphically. This time I'm going to leave it as a negative factor here, 0.002, in the local Y direction. So when I click OK, you'll notice that I've now applied them according to the global Y positive direction. Here's our second orthogonal direction taken into account. And lastly, we have our negative Y, Insert, Loads, Imperfections graphically, positive 0.002 in the local Y-axis direction. So I can turn back off these members here. We can render our sections, turn off the local axis system, and I'm going to cancel this visibility mode, and let's just drop down to one of these load combinations where I've applied the imperfections. So now you can see my dead load, my live load with the appropriate load factors, as well as those imperfections that have been applied. Okay, so that is all that we need to do to account for those imperfections. Let's go back to the PowerPoint again and discuss the modified stiffness and how we can address this in RFEM. Section C2.31. This tells us that we need to apply a 0.8 factor for all axial and flexural stiffnesses to members that contribute to the stability of the structure. Now there is a little note section in the code, and it tells us, well, in order to avoid artificial distortions, just go ahead and apply this 0.8 factor to everything. So this is a very easy way to avoid the artificial distortions. Apply that 0.8 factor to all axial and flexural stiffnesses of every single steel member within our structure. Now there is an additional tau sub B factor for flexural stiffness. This comes from section C2.32. Again, this is just a screenshot directly from the code, and you'll notice that our tau sub B factor has is dependent on our axial loads. So when our required axial compressive strength over the axial yield strength is less than 0.5, then tau sub b can just be equal to 1.0. But the minute that that ratio is greater than 0.5, well, we need to use this equation that's dependent on our axial loads to calculate what the tau sub b factor is, which will be less than 1.0. Again, we have our alpha factor 1.0 for LRFD and 1.6 for ASD. And what we also can do, the code tells us, is that with a tau sub b equal to 1.0 for all of our flexural stiffnesses, well, then we can completely forego this second equation here and apply an additional notional load of 0.001 alpha yi. This is exactly like the notional loads that we saw in the slide before with our imperfections. Now, it is very clear that this notional load is not in lieu of our notional loads from our geometric imperfections, but it must also be applied to our different levels. So what's nice though is that in RFEM we can take this into account. So to me it's almost easier to have the program automate this tau sub b calculation than to go back in and add even more notional loads. So let's take a look back in the program to see how we can apply these stiffness reductions. What I want to do is I'm going to select my entire model. Everything is highlighted in red. And if I right-click on any one of the members, I'll see the member option here and edit. We have this modify stiffness tab, and this is the case for all members within the program. Now the default is set to none, but if I go ahead and open up this drop-down, I will see according to AISC 360, section C 2.32. So we even give you the code reference. Again, this should look very familiar. This is the criteria that we were just looking at directly from the code. Tau sub b factor, we can either set this to iterative. So in that case, it will determine the ratio of my required versus my limit axial compressive forces. Or I can set this equal to 1.0 and then I can go back in and apply those additional notional loads. Again, I think it's almost easier just to let the program iterate and find that tau sub b factor for me. Now notice that this, or just know that this tau sub b factor will only be applied to our flexural stiffnesses, not axial stiffnesses. We need to give the alpha factor a designation. In our case, we're designing per LRFD. Now here is our 0.8 multiplication factor for both our flexural and axial stiffnesses. It's 0.8. This is exactly what the code tells us to do. Notice you can't edit this, and the reason why is because this is what the code tells us to do. So if we're going to design according to the AISC 360, well, then we're going to only put in the application according to the code. If you wanted to do so in some other way for whatever reason, we do have a multiplication factors here where you can go ahead and adjust your stiffnesses individually for the members based on whatever criteria you would like. For our case, we are going to use what the code tells us to do. So now I click OK, and that tau sub b factor and that 0.8 modification factor have automatically been applied to my structure. So after all of that, we are finally ready to run an analysis within RFEM. And I want to let you know that if I select RC1 here, this is my envelope solution for LRFD, and I can begin my calculation. I wanted to make a very clear point that everything that we have done up until now has not even touched any of the add-on modules. So everything we've done for the analysis purposes, including stiffness reductions, imperfections, has all been done in RFEM, our main program. And now we're just running all of our LRFD load combinations to get the analysis results in the program. Now, when I do run a result combination, you can see here that I have a couple different numbers shown here. Well, that's because for a result combination, we give you both the positive and, or sorry, both the max and the min values. You can change that here in our result combinations. Maybe better is to jump to a particular load combination 3, to view the deflections in particular. So after we ran our analysis, we have our results pop up here on the project navigator. Under the Display tab, I want to make it clear that this Display tab really controls everything that you're viewing within this graphics view. So if you're not happy with the basic line elements here for our deflection, under Deformations, well, first we go to Results and we can expand out this tree, go to Deformations, and under Members, we can change this according to how we'd like to view the deformed structure. We can choose cross-section colored here. We can move this back to lines, and this is the case for everything really that you're viewing here. RFEM gives you a lot of control over your results or your input or anything else that has to do with the graphic view. So maybe back on our Results tab, we want to take a look at our members in particular. And so here we can select members, and I'm under Load Case 13 here. And I'm looking at, let's say, our internal forces for our axial loads. So you can see here that, again, this is just a basic view of our axial forces, but if I ever want to change this, I can go back to my display. Maybe I want to view it as a color diagram with some different contours. I can view it without the diagram so that it's a basic wireframe structure, and I can view these different colors here based on the axial loads, or I can even view it as a rendered cross-section. You have complete control over what the scale is here. You can change colors if you would like. So if you can't read something very clearly, again, complete control to change any of that. You can always also right-click on a member and go to the results diagram, and here is going to be a little bit better of a display in more detail. We can add in some, take a look at our shear forces and maybe our bending moments along this particular member. We can even drop down and choose a different load combination if we'd like. So this is a little bit more detailed view rather than viewing everything graphically. If we go back to our Results tab, maybe we're more so interested in our support reactions. Perhaps we'd like to just select one of these moment frames here. We can base it on the visibility of the selected objects. I have the ability to print off this picture here. Again, I can increase font sizes, I can change colors, I can do anything that I'd like as far as viewing these results. So essentially, this sums up the basic first half of the webinar in regards to the analysis. Again, everything was done in RFEM so far, just to take a look at internal forces and how to apply the code standards for the direct analysis method. So let us jump into our add-on module, STEEL AISC. The list of add-on modules are in our project navigator here, and you can see it's a very long list. We have a lot of different international standards. We have a lot of different materials. You can always right-click and add something to your favorites to move that up to the top of the list. We also have the add-on modules drop-down box up in the file menu here, and it is categorized a little bit more clear into different materials such as steel, concrete, timber, aluminum, as well as some other modules. To me, I think it's most efficient to just use this list over here in our project navigator, and I can double-click on my STEEL AISC. A clear distinction here, we are now in the add-on module. And when I say add-on module, it's nothing more than a dialog box within RFEM. So we're not opening up a separate program here. We're just simply launching this dialog box, which is going to take all of my materials, my sections, my loading, my internal design forces into this add-on module. The first thing that I want to do is to rename my case. So this case number 1 here, I'm going to call it columns and braces. So I'm going to design all of my vertical members to begin with. So now I can see right here, case number 1 is called columns and braces. I want to define the members that I would like to design. I'm just going to select all of my vertical members with my selection box. I'm going to do design according to LRFD 2010. We also have the 2005 code available here. Now for my ultimate limit state, I'm going to choose all of my LRFD load combinations. So if I hold down my shift button, I can move those all over at once. Serviceability, this is the reason why we have our ASD load combinations to check our deflections. Then all I need to do is just to simply move down the list. So I take a look at my materials. Well, again, these are brought from RFEM, so I don't need to modify these. I can if I want to, but I don't need to redefine them. So I have steel A992 and steel A36. If I take a look at my cross sections, the only cross sections relevant here are the ones that I've chosen for design under this general data. This is the case for any of our input or our results table, which I'll show you that later as well. But as I click in the tables here, the program is automatically synced up in the background of RFEM to show me exactly where I'm at in the structure. So a small structure, maybe not so useful, but when I'm getting into larger structures, you can see how this can be extremely useful. I can take a look at my cross-section data by just the little info button here if I want to take a look at any of those particular cross-sectional properties. They're also available in my table down here. Intermediate lateral restraints. So this would be if my top or bottom flange is restrained at any point. I will show you this for our next case. I'm going to assume that for my vertical members here, I don't have any lateral restraint for my top or bottom flanges. Effective lengths. This has to do with our effective length factors and our unbraced lengths. And I can't stress enough how important unbraced lengths are. As a software program, the program is only smart enough to know the unbraced lengths as you've entered them into the program. Meaning you can see right now that our unbraced lengths, which would be this column, we have a few columns here, buckling about the strong axis, buckling about our weak axis, torsional buckling, and lateral torsional buckling. We have the column here for our K values and our K times our L. Now this is our unbraced length times our K values. So to begin with, the program will always default to the full member length. And the reason for this is that we don't know connection types. We don't know if there's some type of, I don't know, wall here that is maybe bracing the structure for the weak axis. The only thing that it knows is what you've modeled it as. So I'm not saying that's just for RFEM and our software, but any type of structural analysis software, you really have to pay close attention to these unbraced lengths because they make a significant impact on your member flexural capacities. So one thing to note, I'm going to jump back to the PowerPoint here very quickly, is that the effective length factor in section C3 says that we can use 1.0. This is unless a smaller value is justified, but the conservative approach is to use 1.0. Now this is a very huge difference between the direct analysis versus the effective length method. With the effective length method in Appendix 7, we have to figure out what our K factors are, whether that's the recommended value or the actual value. That's a big difference in the approach between the two different methods. With the direct analysis method, we take all of those uncertainties into account with our stiffness modifications. So this is one big advantage of using the direct analysis method is that I don't have to worry about my K factors anymore. I can just set them all equal to 1.0. So back in the program, you can see that that is the default. So I don't need to touch any of my weak axis or my strong axis or my torsional buckling K factors. If I'm unsure what is strong and what's weak, I have a little graphics view here showing my z-axis, my y-axis. We also tell you in this table buckling about major axis, buckling about minor axis. For the case of these vertical members, I can leave the unbraced length, the full member length that's already default within the program. I'm assuming that it's not braced anywhere else. So now all I need to do is to continue down my list, design parameters. Modification factor C sub B. The program defaults to 1.0. It's a more conservative approach. This comes from Chapter F for our flexural design. We can actually use this drop-down to change this to manually if I'd like to calculate this factor manually, or we can use the equation F1-1. This is where the program will take a look at all the moments across the beam and according to the equation F1-1 come up with the C sub B factor. This way we might be able to get a little bit more of the capacity. Now I can manually change these according to each member here, but an even easier approach if for some of those who are not familiar with it, I can change all my members at once by checking the set input for members number. I have the all checked, but if I wanted to only do a certain amount of members, for this case I want the all checkbox checked. And then using this table in the lower section, I'm going to select according to F1-1 again, and now you'll notice that all my members were automatically changed to take that into account. Now my distance L sub V, this is actually for round HSS members. It's not applicable for our structure today. It does have a little section reference here, distance according to G6. If I go ahead and click in this table and leave my mouse there for just a second, we do get a little note down at the bottom that it is the distance from maximum zero shear force according to G6. Same thing with our gross area, our net area. Leave this in the table for just a minute, and then we get the population of this little note down here, net area according to D3.2. So we're trying to make it as clear as we can where these come from within the AISC code. We aren't going to touch any of the rest of this stuff now. Basically, our areas are all going to stay the same. Serviceability data. If I click my details button here, here is where my serviceability deflection ratios are given. So the default for a simply supported beam would be L over 360, and for cantilevers it would be L over 180. Now we also have the option to show the deformation according to the shifted member ends or the undeformed system. We may know this a little bit better as absolute versus relative, with relative being the shifted member ends and absolute being the undeformed system. For the case of these design of these members, we will leave this as shifted member ends and leave our deflection ratios as is. So now I will select this drop-down box and choose member, and I want to choose my members to design my serviceability state for. I can either choose a single member, a couple members, or I can drag across this selection box and design for all of my vertical members at once. And now you'll notice that this table was automatically populated. Now my reference length again is going to default to the full member length. That's fine in this case. My direction it's going to check for in both the strong and the weak axis direction. If I had a pre-camber that I'd want to take into account for my deflection, I could enter that in here. And lastly, the beam type. These are all simply supported beams on either edge, or they're supported on either side. We could also choose cantilever here if we had a cantilever member type. And now we are finally ready to run a calculation. So this will take just a split second longer, and the reason why is because I haven't solved for my ASD load combinations in RFEM yet. My LRFD we already solved for, so that's bringing those into this add-on module. So we're running the ASD load combinations for our deflection checks, and you can see now that we have designed for all of our members. We have this whole results section available after running the calculation. I can view my designs by load case, so you can see load combination 1, 2, 3, 4, etc. We can also view the design by cross-section. So as we remember, I'm going to exit out of this real quick, and I'm going to change my view. I'm going to go back into the add-on module, and I just want to show you this because if I'm looking at design by cross-section, as I'm in this table, the program will automatically sync up to where I'm looking at exactly. So again, this is nice to see exactly where you're at. So for design by cross-section, we only design 3 cross-sections, so we should only have 3 options available here, which we do. Now, probably the most important one that we'll be referring to a lot is design by member. So this is something that I always emphasize because I think it's such a strong feature of our program. If I take a look at one of my members here, let's say member number 9, first of all, I can see where it's at within the structure. And you'll notice that we give the code check for every single requirement within the AISC. We don't just give you the controlling case. This is so important because as engineers, of course, we're always encouraged to maybe do some hand calcs to make sure that our results make sense rather than just plugging numbers into a software. So when you're doing hand calculations and you think, okay, well, I think a different case should be controlling, well, that's probably available here within the add-on module. And then for each calculation requirement check, we further give you all of the variables that went into consideration for that design ratio as well as code references. We are certainly not a black box program. We try and give the user as much information as we can with code references so that you can understand where your numbers come from. Now you'll still notice that we do have the controlling code check here. We have our green smiley face because we are below 1.0. If I did want to filter these to the max controlling case for every single member, I can do so with this little filter button here. So if I didn't want to see every single check, well, I can filter these out to see which one's controlling for each individual member. If I'm interested in all of them, though, I change this back to greater than 1.0. So something else under the details, we can always control the max allowable design ratio. Typically for design, you don't want 1.0. You want something more like 0.8, 0.7. Well, you can always set that here as 0.8 if you're more interested in seeing which members are above that 0.8 ratio rather than 1.0. Design by X location, this is going to be a little bit longer of a table. What this does is it gives us our code checks along the X length of the member for all the members that we have designed for. Again, useful if you're interested in every little detail about where the numbers are coming from. Governing internal forces by member, well, this is just what internal forces we're designing from, taken from RFEMu. And finally, a parts list by member. This is nothing more than our material takeoff for our different sections. So that basically sums up the check or the first case for our members. So I'm going to run another case, and I just go to File, New Case, and this time we will select purlins. I click OK. It's asking me, do I want to save the changes? Yes, I do. And you'll notice that I have a blank slate again. I can always use this drop down and jump back to my columns and braces, so I don't have to input all that information again. I just want to design a different case here. So for my purlins, I want to use my selection box here. And again, we could create a user-defined view, but for now, I'm just going to hold down my control key to select all of my purlin members. I click OK. LRFD 2010, I'm going to choose my LRFD load combinations for my ultimate limit state design and my ASD load combinations for my serviceability. Now again, we're just going to move down this list. Everything looks okay for our materials. Our cross sections, we're only designing our rectangular HSS members here. Intermediate lateral restraints. This is a case where maybe I have some type of metal deck on my roof, and I know that my top flange is going to be braced at the center point for all of these purlin members. Well, this is where we would define this within the intermediate lateral restraints. So member number 17, you can see it highlighted here. Well, I can click that there is a lateral restraint available, and then I can give it the number of restraints along that member length. You'll notice that the program evenly spaces out those lateral restraints. I have this checkbox checked down here, relatively 0 to 1. This just means that it's going to give me the X location on a scale of 0 to 1, with 1 being the full member length and 0 being the beginning of the member. I can uncheck this if I'd rather see maybe a distance in feet. So like I said, we're going to leave this as 1, assuming that it is braced at the midpoint here. Now again, I could individually put these in for each member, but rather I'm going to use the set input for member number all down here. I just need to redefine these by checking this checkbox here, and I have n equal to 1. Now at the current time, the program will brace both the top and bottom flanges. Available in our Eurocode add-on module, EC3, we have the criteria selection to choose either the top flange, the bottom flange, or both flanges. We know that this is important, and we will implement it into our AISC module in the near future. For right now, you just have to know and keep this into consideration that it is bracing both flanges. If you only had your top flange braced, then you would want to maybe take a look at which flange is in compression and choose the most conservative value here. So something just to keep in mind for this intermediate lateral restraints. Now, if we move on to effective lengths for members, you'll notice that our table should look a little bit different here. For our buckling about the local y-axis, our strong axis, we still have the full member length, 10 feet. That's great. I don't have anything restricting that strong axis bending here. Now, buckling about my weak axis, my local z, you'll notice that my k times L is now set at 5 feet. That's the halfway point. Same for torsional buckling. Lateral torsional buckling is not applicable for these HSS members, so that's why it's grayed out. So the program took this information from the intermediate lateral restraints and applied it to our effective lengths for our members here. So we can simply continue moving on down the list. Our design parameters, again, I'm going to maybe try and get a little bit more capacity out of this by choosing the according to F1-1 equation. Serviceability data, again, I can choose my members here, and I can simply choose all of my purlins by my selection boxes here. Oops. There we go. And you can see the program automatically populates this table. We're using the full member length. We're leaving these details as they are with L over 360, and I can run my calculation. Exact same results that we saw before, but obviously with different member design. But we still have the same layout by load case, by cross-section, by member. We have a controlling ratio of 0.70, which is pretty good for design. So as far as that goes, nothing really too different than our last case. But for our third and final case, I want to show you the difference between sets of members and members within the program. So if I highlight these top members for my moment frame and I right-click, I choose under member, well, I can create a set of members here. Now, I can name this. Right now, it's just named default continuous members, and all of these members are considered for this one continuous member. Now, when I scroll in, I should have a very faint dotted line around all 6 of these members because this is considered a set of members. So what I'm going to do back in the AISC design module is I'm going to create a new case here. And with this new case, we will call it rafters. I want to simply show you the difference between designing a member versus a set of member. So what I'm going to do is I'm going to select these 6 members adjacent to my set of members. Click OK, and I'm also going to select my set of members for design. You'll notice that one click selects all 6 of these because I've defined it as one continuous member. And we're going to see how to do the exact same design for these 6 members versus the set of members, but how our input is a little bit different. So ultimate limit state design, again, nothing different here. We're just selecting our LRFD load combination, serviceability, with our ASD load combinations. Now, you'll notice that we have a few more options here under our list of input. You can see that I have sets of members for effective lengths in addition to members now. I also have nodal supports, member hinges. So moving on down the list, let's just see how we can apply these. So materials, we don't need to touch. Cross sections, we don't need to address this either. This parametric section is simply my tapered section that I've defined near the haunches of this moment frame. Intermediate lateral restraints, I'm going to leave this all empty here. I'm not going to address any of that. Now, my effective lengths for my members. So members is separated from sets of members here, so I'm only dealing with these 6 separate members. You'll notice that this is a case once again where I really need to focus on these unbraced lengths. If I take a look at my little tapered member here, it's telling me that my unbraced length for my strong axis is only 3.02 feet. This is really wrong. My strong axis bending is actually the entire length of this continuous member here, because I have nothing underneath it preventing it from bending in the strong axis. So actually what I want to set this as is 40.7 feet. You'll notice that when I do this, this K column automatically changes to 13.489. At some point in the future, we will implement two separate columns here, one for K, one for L, and then a third that includes the KY times L. For now, just completely neglect that this K value is changing. That's just because our column here that's actually used for the calculations is what's important. Since our K is equal to 1.0 according to the direct analysis method, I'm just multiplying that by the unbraced length of 40.7. Now, the same goes for my weak axis. It's certainly not 3.02 feet, but it's actually this length from here to here where my purlin's framing in to brace the weak axis buckling. So something more like 10 feet. Same thing for torsional buckling. You'll notice that we implement this feature that you can type it in if you'd like, or you can measure it graphically. Lateral torsional buckling, same thing. We want to measure this again to get a value of 10 feet. This is the case for all of these 6 members across here. You know, it's a pretty symmetric structure. So what I want to do is I want to set the input members for all. And again, for my KY times L, I'm going to retype this in so that the program will automatically populate this all. Now again, these K values were automatically affected by my input here, but disregard that this is the important column for our calculations. Now the KZ times L, we have that set at 10 feet. We'll put that in again. 10 feet for my torsional buckling and lateral torsional buckling. So now these are the correct unbraced lengths for all 6 members. Again, this is why it's important that we have to individually look at all of these. If we jump down to my effective lengths for my sets of members, I only have one input. I just have my continuous member here. Well, these are not correct. Sure, my buckling about my strong axis certainly is 40.69. That's the full length of the member. But my Z-axis is not. So I could manually put this in, but rather I'm going to jump right down to nodal supports. So with these sets of members, the program will actually do an eigenvalue analysis. And the reason that it does this is because these continuous members don't necessarily need to be in a straight line. So the advantage of an eigenvalue analysis is that the program will calculate the critical buckling moment in the results for us. That's something that a single member design does not do. And we can also type in or enter in the type of supports of these purlins framing in here. So you'll notice that the program automatically put at the 2 ends a fork type support. Well, I can also put these in where these purlins are framing in, this fork type support. And also take note that I am not putting this fork support where the tapered member transitions into my W shape. I don't have anything bracing it here. Something interesting to note here with the eigenvalue analysis, it will then create a so-called kind of model in the background, an FEA model with 4 degrees of freedom at all of these locations. And something that's not available in RFEM or when we're designing our members individually is warping. If I click within inside this box, I can actually click on the little details button down here at the bottom to open up my warping spring. So I can take into account warping stiffening depending on an end plate, a channel, an angle, and so forth. I give it the dimensions, and then the program will automatically calculate this warping spring for me. Again, this is a huge advantage because this is something that's not taken into account within RFEM. For our case, we don't have anything restraining warping, so we'll leave these just as simple fork supports at these locations. Member hinges, if we had some type of shear release, moment release, warping release, we could also put these in along this continuous member. Now if I jump back up to my effective lengths for sets of members, you'll notice that these are now grayed out. That's because I put in those nodal supports, so the program will now calculate the most conservative value for my weak axis unbraced length as well as my torsional buckling and lateral torsional buckling. So a very effective way to design sets of members. Design parameters, again, I'm going to use this according to F1-1 by setting my input for all and choosing that from my option down here in the table. And lastly, serviceability data. We certainly want to compare how the serviceability checks for both of them match up. So the first thing I'm going to choose is my sets of members. I only have one set of members to choose in this table. I click OK. The reference length is the full member length. That's fine. Now I also want to check my individual members adjacent to it to see if we get about the same results. I click OK. All of those members are populated here, but this time I want to manually enter in my lengths here. The reason for that, I'm going to put in the full member lengths, 40.69. I hit my down arrow key and the F8. F8 will automatically populate those. The last thing that I need to do is to go into my details, and I need to change this to my undeformed system. The reason why is I need to compare apples to apples here. I can't compare to the shifted member ends because I'm taking a look at deflection of these individual members versus one continuous long 40.69 foot member. So I'm going to change this to undeformed system. I click OK, I click calculation, and now the design is done. Again, just like our input, we have a few other options here. We have design by sets of members. We also have design by member. So probably the easiest way to compare how these two values are matching up, our individual members versus our sets of members, is just to jump into our graphics view. You'll notice that for our graphics view, we're still in the results, but right now I'm in the STEEL AISC module. You can also tell that with this drop-down button here. I can easily jump back to one of the load combinations to see my analysis results in RFEM, but as long as I'm under the STEEL AISC, that means that I am still within the add-on module. The results available are much more simplified. I don't have this long list of options because I'm only viewing the code checks. So if I take a look, you'll see let me go ahead and highlight just these two that we were designing to make it a little bit more clear. And I take a look at my ultimate limit state design, 0.2, 0.2, that's great. I should see exactly the same results. I take a look at my deflection checks, 0.82, 0.81. Very, very close. Remember, this is an asymmetric structure because of our lateral bracing here. So I'd say that this is pretty good results. So I just simply wanted to show you guys how you could easily design a set of members versus individually designing the members. Both have their advantages, but certainly set of members maybe gives you a little bit more options in terms of warping. Now, the last and final thing to do is to quickly show you how to optimize. Well, for this, I'm going to jump back to columns and braces. So these are my vertical members that I'm designing. Let me click OK and cancel my visibility mode here. I'm going to turn off my results. Going back into my STEEL AISC. Under columns and braces and cross sections, we have a column here called optimize. So we get asked all the question, well, do you do optimization? Well, yes, we do. If we use this column in the drop-down box, I can either optimize from the current row, which this means it will optimize from all W shapes within the AISC module. Now, if I wanted to limit that down, I could use a favorites list. So what is a favorites list? Well, favorites list can be done either here in the module with these three dots, or when I'm creating my structure, I can also utilize a favorites list. A favorites list down here at the bottom, I could create a new favorites list, title it 8 by something. If I wanted to optimize only my 8 by something W shapes, well, I can go ahead and uncheck all of these members here and only select my W 8 bys so that I can optimize within these particular sections. For this particular case, we will optimize from the current row, so I want the program to pick whatever is most beneficial in terms of weight for the cross-section. Now, I click calculate, and you'll notice that it takes a split second. The program comes up with 0.97. Something to note about optimization, that this is just an approximation. If I go back to my cross sections, you'll see that the program optimized my previous 8 by 50 into a W 6 by 16. What the program's doing, it's still taking the internal forces based on my old section to do that approximate member design of 0.97. If I go back to my cross sections, it's bright blue. The program gives me a warning. The cross section in RFEM is different from the cross section in RF-STEEL AISC. This is important. This isn't my final answer, this 0.97. This is not the final results. So what I need to do is I need to right click on this blue cell, export cross sections to RFEM. It's asking me to clear my results, and I need to rerun the calculation. The reason for this is that the program has now exported these W6x16s into my overall structure. It's rerunning all of my LRFD, my ASD load combinations with that new shape. It's going to take those internal forces back into RFEM to give me my accurate code check. So chances are we're going to see something other than 0.97. The 0.97 was just an approximation. So when we rerun this, we can take a look. It certainly is different. We now have a check of 0.79. This is closer to 1, so we even have the ability to go into cross sections and optimize again if we'd like to, an iterative process until we find what we would like to use in the structure. So that's a short and simple way of how to optimize within the program. That essentially wraps up the webinar for today. For more information, you can certainly visit our website at dlubal.com. We have more information on RFEM, on the add-on modules that you saw today, as well as many other materials and design modules. We also have a lot of social media sites. I certainly want to encourage everyone to go to our YouTube site, for example. This has all the previously recorded webinars that you can search by keyword. Our Dlubal blog has a lot of frequently asked questions. Again, you can search by keyword. Our email for our Philadelphia office is info-us@dlubal.com, and the phone number here is 267-702-2815. We will certainly have more upcoming webinars. We post them on our website at dlubal.com under support and learning webinars. As most of you know from today, I typically send out an email as well with the invite information. If you are wanting PDH credit for today, please email me at info-us@dlubal.com and just let me know who was in attendance, and I will be happy to issue that certificate for the webinar. And with that said, I want to thank everyone for attending today, and I do hope to see you at the next webinar. Thank you.